That is methods of structural analysis. So last class we have briefly introduced the matrix methods, the types of matrix methods, namely matrix flexibility method, matrix stiffness method. We have discussed about static and kinematic interfaces. What is a flexibility matrix? What are flexibility coefficient? What is a stiffness matrix? What are stiffness coefficients? And what about the size of flexibility matrix and size of stiffness matrix? All those fundamentals we have discussed in the last class. And also we have discussed about coordinates and other basics that are needed for the matrix methods in the previous class. Now in this lecture today we will take up generating flexibility matrices. We know that size of the flexibility matrix for determinate structures will be equal to n by n, where n is the number of coordinates. I told you number of coordinates will be arbitrary, you can choose any number of coordinates. So you have to assign coordinates where measurements are decided. That is, you may apply your force and write out the displacement, or apply displacement and write out the forces consistent with the displacements. So coordinates we fix. Suppose you choose 3 coordinates, then the size of the flexibility matrix will be 3 by 3. That is arbitrary. You can increase or you can decrease. And also, what is coordinate? Already we have discussed. Right. Now, let us take a simple example here. Cantilever. We are going to deal statically determinate structures first. This is the cantilever of span L. Yes. Let us choose this as coordinate 1 and this as coordinate 1. So we have to form the flexibility matrix for this. There are 2 coordinates, therefore the size of the flexibility matrix will be 2 by 2. So the A matrix will be consisting of 2 columns A11, A12, A21, A21. Now, for getting the first column, you have to apply unit force along coordinates 1 only, unit force along coordinate 1 only, and write out the displacements along coordinate 1, and you know the flexibility coefficient is, this gives a displacement at coordinate I due to unit force at coordinate J. Now, for getting the first column, apply the unit force along coordinate 1 only. This 1 stands for unit force. This stands for unit force. Right. Now, so this will form different shapes will be like this. This is one displacement. The other one is corresponding to the coordinate 2 will be a rotation. Right. So corresponding to 1 it is displacement. Now this is the displacement along coordinate 1 due to unit force along coordinate 1. This is the displacement along coordinate 2. This is the coordinate 2 rotation. So rotation or displacement along the coordinate 2 due to unit force at 1. So this will form the first graph of flexibility matrix. Now for getting this, we are going to make use of the methods that we have studied earlier. Now we will adopt the moment area method. So for getting the displacements, so this is the bending moment diagram. Bending moment diagram is 1 into L into the maximum bending moment. So this is 1 into. So EA is uniform. EA is uniform. Therefore, the M by EA diagram will be 1 into M by EA. This is the M by EA. Now, A11, it is a displacement along coordinate 1 due to unit force at 1. For getting the displacement, you have to get the moment of area of the M by A diagram. Moment of area of the M by A diagram will give you the difference like that. Point under consideration. So, this is a triangle. So, area of the triangle is equal to half into L into half into L into L by E. Half into L by E is the area of the triangle into its moment. So, the distance from this center of gravity, we get this is a 2/3. So, moment of area will be given by area multiplied by 2/3. So, we can simplify this. This is equal to L into pi. You know, the force is W. Say W L by 3A. Here the force is unity. Therefore, it is L by 3. So, A1 equal to A. So, next A21. A21 is the rotation. That is given by half the slope of rotation. That is given by the area of the M by A diagram. So, A21 rotation or displacement along coordinate 2 due to unit force along 1 is given by the area of the M by A diagram. That is equal to half into L into L by A. That is equal to L square by 2. So, here first column is equal to L cube by 3A L square by 2. That is the first column. For getting the second column, you have to apply the unit force along coordinate 2. Second column. Then apply unit force along coordinate 2. Along coordinate 2. Apply unit. This 1 stands for unit force. Unit force along coordinate 2. For that, we know the bending moment diagram will be a rectangle. So here it is 1. Now here it is 1. Sir. So the M by E diagram will be 1 by E. So apply unit moment. If you apply a moment equal to M, the moment here will be M. Since we are applying only unit moment, it is 1 by EA. We are getting a M by EA diagram. M by EA diagram. M by EA diagram. Right. Now, A12 is 1, 2. Okay, this will also have the different shape like this. This is the displacement along coordinate 1 due to unit force along coordinate 2. Similarly, here this is the displacement along coordinate 2 due to unit force along coordinate. So you get A12 and A22. So A12 is a displacement. Displacement is given by moment of area of the M by A diagram. So the point at the. So So area is equal to L into 1 by A. L into 1 by A is the area of the M by A diagram. You are taking moment about this point. So into L by 2 because it is a rectangle. So into L by 2 that is equal to L square by. Then A22 is the slope or rotation. That is given by the area of the M by A diagram. Area M by A diagram is given by length is L, area is 1 by A, so that is equal to L by. Therefore, the second term of the flexibility matrix will be L square by 2EI, and L by E. That is about the flexibility matrix for the given cantilever with the 2 coordinates. So you can take some L and A outside, or you can have it as it is. You can simplify, otherwise you can leave it as it is. But the property of some of the properties of flexibility matrix are, one is the leading diagonal values. The leading diagonal values will be positive different. Will be positive. So this is positive. This is also positive. The other one is, it is a symmetric matrix. A12 equal to A21. It is a symmetric matrix. These are some of the properties of flexibility matrix that we have to understand. So that is the first example. We will take the second example. Let us take one more cantilever. With the 2 coordinates. Coordinate 1, coordinate. This is here. A is uniform. This is example. How to find out the flexibility matrix for this structure? So here again, we have chosen 2 coordinates. Therefore, the size of the flexibility matrix will be 2 by 2. 2 by 2. So A will be consisting of first column, you apply unit force along coordinates only. So this one stands for unit force. You are applying unit force along coordinate one only. But here, this is the different shape. So this is the displacement along coordinate 1 due to unit force along coordinate 1. Coordinate 2 is here. This is the displacement along coordinate 2 due to unit force along. You apply unit force only along coordinate 1. Find out the displacement along unit coordinates 1 and 2. So for getting this, the bending moment diagram, as we have done earlier, known to you now, this is 1 by A. 1 by A. Bending moment is 1 into L. So L by A, as we have done here, L by A. So this is M by A diagram. By A diagram. already we have calculated. So this calculation is not to repeat. So A11 equal to L2 by A11. A21. A11 already we have calculated. A21 is a displacement here along coordinate 2. So you have to find out the displacement here at this point. So displacement here is given by, let us first divide the trapezium. That is area of this trapezium, moment of area of this trapezium about this, because you want deflection. A2 is a deflection. So the deflection here is given by moment of area of this trapezium about this point. So let us divide this into a rectangle and a triangle for convenience. So we will take moment of area. This is L by EA. This is half. That is L by 2. It is half of L by EA. Half of L by EA. So here also this is also half of EA. The reason is this is L by 2, this is also L by 2. This is also L by 2. Right. So A21 for this section, for the rectangle, it is L by 2 into L by 2EI. L by 2 into L by 2EI into half of L by 2. Because this is L by 2, this is also L by 2. Half of L by 2. So this is the area. Area of the rectangle is L by 2 into L by 2EI into half of L by plus. For the triangle, it is half into L by 2 into L by 2EI. Short side of the moment of area, you will get this 2 of L by 2. 2 of L by 2. So that is equal to, so it is L cube, right? 16EI plus L square by 8EI into L by 3 equal to L cube by 8EI plus L cube by 24EI. 48 here. LCM 3L2 plus 2L2 equal to 5L2 by 48. 5L2 by 48. So A21 is equal to 5L2 by 48. Therefore, the first column is L2 by 3A, 5L2, that's about the first column of the flexibility matrix. Second column of the flexibility matrix, second column is not applied. Unit 4, the wrong coordinate 2 only. to indicate unit force. You are applying unit force along coordinate 2 only. 2 only. This is L by 2. L by 2. So here also the different shape will be after this it will be a straight line. So this is the displacement along coordinate 1 due to unit force along coordinate 2. Here this is displacement along coordinate 2 due to unit force along coordinate. So you have to remember that definition for the flexibility coefficient. So the bending moment diagram will be, because this is the total point, right? This is the bending moment diagram. So the triangle with the contrary load at the center, it is the bending moment is 1 into L by 2. 1 into L by 2. So it is 1 into L by 2. So L by 2, then by EA. So M by EA diagram will be L by 2. L by 2 EA is the M by EA diagram. M by EA diagram. So now we have to find out A12. A12 is the displacement. The coordinate 1 due to unit force along coordinate 2. So the displacement here is given by again the moment of area of the M by A diagram about this moment of area of the M. So area of the M by A diagram will be, it's a triangle. So it is half into L by 2 into L by 2A. This is the area of the M by A diagram. You want to comment about this point. So it is L by 2 plus 2 of L by 2. That is L by 2 plus 2 of. This is equal to L square by 8dl into, so L by 2 plus L by 3. L by 2 plus L by 3 will be 6 3L plus 2L 6. So 3L 2L equal to 5L plus 6. So into 5L plus 6. What is A? That is A12. A22 is equal to the displacement at this point. So displacement here is again M by A diagram. So area is half into L by 2 into L by 2EL. When you want to comment about this point, it is 2/3 of L by 2. 2/3 of that is equal to L cube by 24. So that is the displacement along coordinate 2 due to unit force along coordinate 2. That is A22 is equal to L cube by 24 EA. Therefore, the second column of the flexibility matrix will be A12 is 5L cube by 48 EA. 5L cube by 48 EA. L cube by 24 EA. So here also you can check the values along the leading diagram are positive definite, and this is A21 which is equal to A12. This is a symmetric matrix. This properties you will have to check, so that if there is any mistake in the calculations, you can always correct it. Then and there. This matrix is very important because we are going to use this matrix in all problems on continuous beams, portal frames. Simply writing the matrix and that is part of the problem. Part of the problem will be repeatedly using this. So, A11. So there are two coordinates. Therefore, the size of the matrix here will also be 2 by 2. Because there are two coordinates. So we know for getting the flexibility matrix, we will apply the unit force along the coordinates one at a time and get the displacements along the coordinates one at a time. Now for getting the first column, let us apply unit force along coordinate one only. Let us apply unit force along one only. So unit force along coordinate one only. Right. So this is actually distance for 1 unit. You know, we are following generalized coordinates. Stands for a moment. That's all. Moment is also considered as a force in generalized coordinates. Right. What? Now, when you apply unit force here, the moment diagram will be a triangle. Maximum 1 here and 0. So if you want to check it, what you do is, this is the moment. This is the moment. 1. So the reaction here, this is clockwise moment. So for anti-clockwise moment, this reaction will be downwards. This reaction will be upwards. So the reaction here will be 1 by L. Here also will be 1 by L. So if you take moment about any section, it is 1 minus 1 by L into S. If you do it, you just get a linear diagram and at that time it will become 0. Take moment and substitute different values of S and substitute L, you will get the value will be equal to 0. You can always check it by finding out the reaction. Because any element or any structure, you have to satisfy all the 3 conditions of equilibrium. Sigma V equals 0. So these two will make sigma V equals 0. This alone cannot make anything but the equilibrium, because subjected to a clockwise moment of variety, there must be an anti-clockwise moment of variety that will be given by these two reactions. These two reactions, 1 by L into 6, 1 by L into L. 1 by L into L will be 1. So this is plus 1, this is When I apply that moment, the meaning of this diagram will be clear. It is 1 here and it is 0 here. So this elementary calculations you will be able to do and understand this problem. So this is 1. Right. This is the bending moment diagram. So EA is uniform. Therefore 1 by EA is the M by EA. When applied unit force along coordinate 1 only, this is the M by EA diagram. Now you are studying conjugate beam. When the given beam is a simply supported beam, the conjugate beam will also be a simply supported beam. Suppose if it is a cantilever, like this. In the given beam, in the conjugate beam, the fixed end moment will become the free end, and the free end will become the fixed end. So this is the given beam, this is the conjugate beam. But as far as simply supported beam is concerned, the conjugate beam will also be a simply supported beam. Now, after drawing the M by EA diagram, you know that the conjugate beam will be loaded with the M by EA diagram of the given beam. That is, the conjugate beam will also be a simply supported beam. This is the conjugate beam. It will also be simply supported. It will be loaded by the M by EA diagram of the given beam. So the M by EA diagram is this. And this is a sagging moment. This is a sagging moment. Therefore, this will be downwards. The conjugate beam is loaded with the M by the conjugate beam. Loaded with the M by EA. Now, you want the displacements along the coordinates. That is, this is coordinate 1. So the displacement here is a rotation. This is A. This is A. Along coordinate 1, due to unit force along coordinate 1. Now, this is A. Displacement along coordinate 2, due to unit force along coordinate 1. Now, only unit force along 1 only, A11 and A21. So, we want the slope here and we want the slope here. Right? Already we have studied that the slope at any section of the given beam will be given by the shear force at the corresponding section of the conjugate. Conjugate will be loaded with the M by EA diagram of the given beam. Find out the slope at the corresponding section. The shear force at the corresponding section will give you the slope here. Now we will do the calculation. This is 1 by EI. 1 by EI. Right? Now what about RA? Now RA into L minus. So they take moment about the right support. RA in L minus half into L into 1 by EI. The area of loading into from here to the L. RA in here minus this is equal to 0. RA into L is equal to L square by EA or RA L by L. You can cancel RA equal to L by 3A. The reaction here 1 by A is the total load minus RA. Minus RA is L by 3A. Equal to 6. Here this L by 2EA. Therefore 3L. 3L minus here this 2L. So RB equal to RB equal to therefore there is a reaction. Now you have to draw the shear force diagram for this. Draw the shear force diagram for this. The shear force diagram for this will be RA. What about the variation? How the shear force diagram will vary? It is a constant load. Constant load, it will be alright. This is very fine load. For UDL, what will be the variation of shear force diagram? You recall your memory? You recall? Right. So, constant linear variation. This is uniformly varying load. Uniformly. So, how the parabolic second degree variation? So, you will have like this, and this is RA. This is L by 6A, this is L by 3A, L by 6. Of course, here our objective is not to find out the variation. We want the shear force here. We want the shear force here. So, the shear force at the left support of the conjugate beam will give you the slope of the corresponding section of the original beam. So we want A11, A11 is the slope at the left support of the original beam. That is given by the shear force at the corresponding section of the conjugate beam. So it is L by 3A. Similarly, we want the slope here at the right support. That is A21 we want. So A21 equal to L by 6E. Right. One more point to be noted here is what is the sign convention that we follow in the for shear force? Left up is positive. Right? Down is positive. Left up, right down is positive. Now here, it is right up. Here it is. Left up is no problem. It's not a problem. Right up, the shear force here is right up. Therefore, this is negative. That is it is right. Right up is negative. Right up is negative. So that is about the first column of the flexibility matrix. So the first column of the flexibility matrix minus A2 only. Now, this is the bending moment diagram as we have discussed earlier. As we have discussed in this case, we are applying unit moment right support, getting that bending moment diagram. Now, since this moment is applied clockwise, this will cause a arcing moment. This will be a arcing. This is a sagging moment. So here, this is the sagging moment. This will cause a sagging moment like this. So that will cause a arcing moment. Therefore, the rolling will be up. So this arcing. So this is 1 by EI. This is 1 by EI is the M by EI diagram. M by EI diagram. So why it is triangle, why it is having linear variation already discussed. I think I did not explain again. So we can understand. So that is arcing moment. Now, because of this loading, we want this slope. This slope is A along coordinate 1 due to unit force along coordinate 2. This is equal to this slope is the slope along coordinate 2 due to unit force along coordinate 2. That you have to find out. So for getting the slopes, you are going to draw the conjugative. You are going to load the conjugative with the M by A diagram. Get the shear force diagram from which you get the slope. So, what do you know? Conjugative will also be a simple isomorphism. We load the conjugative with the M by A diagram. Now here, both reactions will be downward. First, you can always write down, even if it is that is, let us assume RA, there, it upwards. Now, when it takes moment towards the right support, it is RA into L plus. So this is also clockwise. When you take moment about the right support, that also causes clockwise moment. RA here plus half into L into 1 by EI. When you take moment about this support is 1/3 of L into 1/3 of L is equal to 0. Therefore, on simplification, you will get RA to be minus L by this plus, when you take to the right hand side, you get minus, so you get minus L by 6EI. That means your assumption is wrong, RA is not upwards. Either you can say, you can mark the arrow upwards and then say it as minus, or RA dash is equal to downwards. And here will be upwards. It's upwards. It's upwards. Downwards it is 3. So, second area. Again, when you draw the cell force diagram, it is like this. So, the slope here, A12 equal to L by 6CA. A13 equal to L by 6CA. A22 directions are downwards. So here it is left down. Left down is negative. Therefore, this sum is negative. So A12 is minus. A22, it is right down. Right down is positive. Left up, right down is positive. Therefore, it is L by 3. So it is A. Therefore, it is minus L by 6A. Minus L by 6A. L by 3A. L by 3A. L by 3A. Let's support the flexibility matrix for the given simply support the tree. L by 6EI into, so multiply this by 2, divide by 2. Multiply this by 2, divide by 2. For L by 6EA, this is 2, it is minus 1, this is minus 1. This is so, in all problems of continuous rings and orbital rings, we will simply write element flexibility matrix is given by L by 6EA, 2 minus 1 minus 1 2. We will use in all problems. You have to remember this matrix. So this is for a simply support to the two coordinates. Similarly, we have got portal frames, determinate portal frames, etc. Which there are a number of examples. Say a can given with the four coordinates 1, 2, 3, 4, and similarly a rectangular with a varying cross-section. Several problems are available in the book. You can just go through. But all if you have any doubt, you can come and discuss. Right? So with this, we just simply introduce. We have solved all kinds of problems. Introduce the method how to generate flexibility matrix for determinate structures. So I am expected to go through other problems and come with the doubts if any.